Your homework is to memorize this and write it 15 times.
Welcome to the coolest, hippest half hour of fun on TV. This is Brain Stew with Jennifer Pulley.
If you are watching Brain Stew right now, then you must have electricity going through your home. But how does electricity get there? Today, Brain Stew visits a nuclear power plant to find out how electricity travels from a power plant to your home. It's a snap. Plus, we jump over to NASA Langley Research Center to meet Rick. Rick is a cool electrical engineer with tons of shocking information on electricity to jolt your brain. The only way I'll let you miss this episode of Brain Stew is if your power goes out. But don't count on it. Brain Stew is next.
Hey you, welcome to another shocking episode of Brain Stew. This week we discover electricity.
What is electricity?
Good question. Let me explain. You've heard of energy, right? Well, energy is the ability to do work. We use energy all the time.
Yeah, like when I run or ride my bike.
Right. We also use energy to turn on a television or a lamp. That energy is called electricity.
Electricity is like a type of energy. It's like food or gasoline. Now, we eat food, like this banana here, so we can get energy, and then we can bounce around and run and walk and do things. Fun. Okay, I've calmed down a little bit. I don't have that much energy. Well, let's talk about your parents. Your parents use energy. They use gasoline to keep their cars moving and their lawnmowers mowing. So what's the difference? I'll tell you. Electricity is a type of energy that you can't see. Well, unless you're watching a lightning storm. Maybe we'll talk about lightning in a minute. We can see energy like food and gasoline, but electricity, it's way different. Yoo-hoo, over here, it's time for a science lesson. Now, you know that anything that takes up space is matter. You, me, air, water, it's all matter. And you should also know that matter is made up of smaller and smaller bits called atoms. Atoms. Now, these tiny little things called atoms are kind of like Legos. Yeah, they're like building blocks. They make up about everything in the entire world. Think you can't get any smaller than atoms? Well, think again. Atoms are made up of even smaller bits called
Electrons and protons. Wow.
bingo. Now, electrons have a negative charge and protons have a positive charge. Sound familiar? Well, it should sound familiar. Now, today we're going to be talking about electrons, these little guys right here. Electrons move in paths around the center of an atom, but sometimes electrons will fly or even jump off of their path to join another atom. Hey, that's what electricity is. Electricity is made of moving electrons, and they're so tiny, no one, not you and not even me with my super-powered glasses, can see electrons. They're so tiny, but they're there, and they move super fast. I mean, those electrons are moving so fast, you might as well say they start and they get there at the exact same time. And those electrons, I mean, they can't sit still. They love to move as much as they can. Shocking, isn't it? Speaking of shocks, have you ever rubbed your feet across a carpet or a rug and then touched a metal handle? Yeah. Oh, you got a shock, right? Well, what actually happened was the electrons were moving through your body and they jumped out of your finger onto the handle and it gave you a shock. Ouch. Sparks are moving electrons.
Now, things like our TV or dishwasher don't get their energy from jumping electrons or sparks. You see, when millions of electrons flow smoothly, we have an electric current. Electric current is what flows through most of the appliances in your house. Well, that is, when you turn the appliance on. See? Electric current is flowing. Now it's not. Get it? Good.
Speaking of electricity and electric current, have you ever wondered how you get electricity into your home? Well, I'm here at Virginia Power. Virginia Power is the power company that supplies electricity to the whole state of Virginia and elsewhere. My friend Carol, she works right here at Virginia Power, and she's going to tell us how electricity gets from a power plant to our house. Let's go. Get out of the way. Glad to be in from that heat. We are inside Virginia Power, and guys, this is my friend Carol.
Hi, Jennifer.
How are you?
Fine. Welcome to Virginia Power.
Thank you so much. I have a question for you.
How does Virginia Power make the electricity that runs in our home?
Well, Jennifer, we make electricity in a number of ways. Our nuclear plants use uranium as a fuel source, and our fossil fuel stations use coal, oil, and natural gas. And of course, our hydro stations use falling water.
So Virginia Power has 3 types of power plants. Hydro plants, which use water, fossil fuel plants, which use coal, oil, or natural gas, and where we are today, nuclear power plant. Now, Carol, those are our 3 plants. Can you tell me how each plant works?
All of the power stations use water. The nuclear stations, which use uranium as a fuel source, and the fossil fuel stations, which use coal, oil, and natural gas, all make steam to turn a turbine, to turn the generator, to make electricity. And in our hydro station, we use falling water to turn the turbines.
So all 3 power plants use water,
That's correct.
but only 2 use the water to make steam.
That's right.
How does electricity get from the power plant to my house?
Power gets from the power stations to your home through a system we call transmission system. The electricity leaves the station and goes on the transmission lines or wires to your home or to industries.
From the transformer to the transmission system to the substation to our house. Whew. And how fast is this stuff? Carol, this looks like it's taken an awful long time.
Well, actually, it's at the speed of light.
Can Virginia Power share electricity?
Oh yes, it can share electricity. If it's very cold up north, we can send power on our transmission lines to them so their customers can heat their homes and wash their clothes and cook their food. And if we need power, that they can send us electricity so that we can use it for our customers.
Wow, so I mean, we could be getting electricity from another state.
That's right.
So electricity gets to our house like that.
That's right.
Then we got all this electricity coming into our house.
How is electricity measured?
Well, if you use 1,000 kilowatts per hour, that's the average amount that an individual or a household uses in one billing cycle, which is for 1 month.
What is a kilowatt hour?
Kilowatts is the same measurement as 1,000 watts. So if you have 10 100-watt light bulbs burning for 1 hour, that's a kilowatt, and that costs about 8 cents.
Wow, 8 cents per hour. Is that
Right.
right? Carol, I'm so excited. There's math involved here. Okay, you said that if we take 10 100-watt light bulbs,
Right.
okay, that's a kilowatt.
That's correct.
That's 1,000 watts because 10 times 100 is 1,000. Okay, so that's a kilowatt. And if we burn those lights for 1 whole hour, that's a kilowatt hour.
That's right. You got it, Jennifer.
Well, I'm a math teacher. I should get this. How do they know how much electricity I'm using? How does Virginia Power know?
Well, in all of the homes and industries, they have a meter, and that meter measures how much electricity that person uses.
Okay, so if your meter spins really slow,
And you don't use very much electricity.
okay, but it's booking like that,
You use a lot of electricity.
okay, and obviously your bill's going to go up.
That's right.
Can you store electricity?
Sure we can. In small amounts though. Batteries can store enough energy to power this flashlight here. Or you can start a car with a battery or run a radio. But for large amounts of electricity like we use in our homes to wash our clothes or cook or turn on the lights, that it has to be made instantaneously and then used.
Now, when I teach electricity in my classroom, I always teach about these 2 kind of things, insulators and conductors.
What are insulators?
An insulator is anything that electricity cannot pass through. Things like glass, rubber, and ceramics.
What are conductors?
Conductors actually carry electricity, and conductors are anything that electricity can pass through. Metal is the best type of conductor. Copper wires, good conductors. Aluminum wires actually take the electricity to your homes.
How can I be safe around electricity?
Well, electricity can be very dangerous, and things that we need to play it safe around are like utility poles. We should never climb on those. Never go around fenced-in areas that have electrical equipment inside. Always read the safety signs. We should also never swim when we hear thunder.
Because that means lightning's not too far away,
That's right.
and lightning is a form of electricity.
That's correct.
Okay, so we don't want to play around substations or anything like that.
That's right.
How does a nuclear power plant work?
Well, inside of a nuclear reactor are these fuel assemblies, and inside the fuel assemblies are little tiny pellets that are stacked on top of each other. And these pellets are uranium fuel. And at our Surrey Power Station, these uranium fuel pellets actually produce heat for us, and that's what we want, to heat water to eventually make steam, to turn the turbines, to turn the generators.
How does a coal power plant work?
The coal is actually burned to create heat.
Okay, yeah, because coal is familiar to us. You know, most of us know, most of us have never heard of the uranium pellets before,
Right.
but uranium is an element, okay, that is used to create heat.
That's right.
Correct. What an electrifying tour. Thank you, Carol.
You're welcome. I'm glad Brain Stew could come out.
Oh, this is so great. Now I know everything about electricity. Well, just about everything. Don't go away. Up next, we act like electrons and jump on over to NASA Langley Research Center in Hampton, Virginia. You gotta meet my friend Rick. He works at NASA, and he's got a lot of cool things to show us about electricity. We're back with my friend Rick. Rick, what's up?
Not much.
How are
Glad
you?
you guys can come out to NASA and join us to do some demonstrations for electrical properties.
I'm so pumped. Now let me ask you a question here. You're an electrical engineer at NASA.
Correct.
What does an electrical engineer do for NASA?
Well, basically what we do is we have the responsibility for providing all the electrical and electronic systems for the center. This would include all types of devices such as low and high-speed tunnel drive systems for the wind tunnels. This has to do with communication systems for power distribution, basically anything that supports electrical needs for the center. We also support satellite communication systems for the space program.
So like these lights right here, this is you guys?
These lights are us.
You're providing the light here.
Definitely.
Okay, that's good.
Didn't Ben Franklin have something to do with electricity?
He was a famous scientist that did the famous kite experiment. He thought that electricity was lightning and lightning was electricity. So what he did was he flew a kite and put a key on the end of it and tried to be able to pull the lightning from the sky, which he did successfully.
That's not too smart though, is it, Rick?
No, not smart at all. A few other people tried his same experiment and they weren't as lucky as he was.
Uh-oh. Was Ben Franklin an electrical engineer kind of like you?
Well, with all his contributions to the study of electrical phenomena, I would definitely say that he was a pioneer electrical engineer.
But you wouldn't go fly a kite and all that.
No, I definitely would not do that.
Is lightning a form of electricity?
Yes, it is. Lightning is a dramatic example of static electricity. It's very similar to like when you're walking across the carpet, you scuff your feet, and then you touch a metal object and you get spark.
Okay, so it's kind of the same thing. We've got some other things too with static electricity,
Exactly.
right? What's this huge piece of foam for?
That's just a piece of foam, and basically styrofoam, when you rub it up against your hair and such, it definitely makes the electrons get very excited and move around.
So you just rub it on top of my
Rub
head?
it on top of your head. Yeah, basically what you're doing is you're pulling electrons off the foam off of your head into the foam.
Rick, you have some milk here at NASA that we can fix ourselves a little bowl of cereal here?
If we go over to the cafeteria, I'm sure we can find some of
All
that.
right, we can do that. Well, but first, let's do this static electricity experiment. We're going to pour some of that on the table, I suppose.
Yeah, basically what we're going to do is pour some of this puffed rice on the table, and you're going to be able to generate a static electricity on this plastic wrap, and then you'll be able to pull the puffed rice off the table. Basically what you're doing is you're taking electrons off of the paper towel and putting it onto the saran
Even though I
wrap.
can't see them, that's
You
what's
can't
happening.
see them, they're so small you can't see them.
Okay, so I charged it real well.
All
All
right.
right, why don't you get that in? How about
Okay.
that? Those are cool. Look at that. You're like making this happen. Do it on this. Rick, that puff rice experiment was pretty cool. You got another one for me on static electricity?
Right, the same type of thing. What we're going to do is pour a little bit of salt.
You like this food stuff, don't you, Rick?
Of course, food is great.
Yeah, I guess
Pour a little bit of salt on this construction paper here. And then what you're going to do is take this rubber comb, and you can rub this wool scarf on it and generate a static charge on that also.
All right.
You should be able to pull that salt right off the paper.
Will any scarf work, or does it really need to be wool?
It needs to be wool.
Everybody could try this one at home. This is so easy, huh?
And if you have really dry hair, you can comb your hair and it would probably work just as well.
Huh.
So what are you saying there, Rick?
All right. And you just hold it over the salt? That's it.
Should be able to hold over the salt.
All right. Let's see. Oh, Oh, cool. Now, Rick, tell me why again? Why is the salt attracted to this comb again?
Basically, what you have is a bunch of electrons that are formed on the comb, and it's attracting particles of the opposite charge,
And
which is the
opposites?
salt. Opposites attract.
Cool. Protons and electrons are attracted, right?
Correct.
Cool. You guys can try this at home. This is really easy.
How does lightning form?
Basically, what happens is you typically refer to lightning as a big spark from the clouds to the ground.
Yeah.
So what it is clouds are big piles of electrons that form inside the cloud. And when they mix in the sky, what they do is they repel from each other because like charges repel.
Exactly.
And as they repel from each other, they work their way down towards the ground. Once this charge gets high enough to break down the air or ionize the air with the positive ground, the electricity jumps across and creates a circuit. And that's where you get the spark and the flow of electrons flowing from the clouds to the ground. And when they flow, they bump into air molecules and they heat it up 5 times greater than the sun. And because of this sudden increase in temperature, you hear this shock wave called thunder.
So basically, the clouds are negative, the ground is positive, and then they attract, and that's what forms the spark. All right, cool. Do you have a cool thing you can show me, like on lightning?
Yeah, we can use this Jacob's ladder over here to kind of demonstrate the same principles. Basically, what you have is
What do
you
you
have
call it? A Jacob's ladder?
Jacob's ladder.
Okay.
And basically what it is a transformer that has a negative electrode and a positive electrode. And basically you have these 2 wires coming up called electrodes. And what we're going to do is we're going to make the negative electrons compile on this electrode here, and they're going to jump across, and then it'll work its way up.
Kind of like what happens when we see a lightning storm with the clouds and the
Exactly.
ground.
Pretend
Okay.
like if we tilted this up, this would be the cloud, and this would be the ground.
Clouds, ground. All right. Oh, wow.
Basically what's happening here is the negative electrons are jumping across to the positive electrode.
Okay.
And that creates an electric circuit. The air is being ionized in between there. And as the air heats, it rises up and eventually gets to a point where the voltage potential between the 2 electrodes is not high enough, and it breaks down in the air and it starts all over again.
Did you get that? That's how lightning forms. Why don't we use lightning in our house then?
Well, unfortunately, lightning is such a great force of energy. It's uncontrollable, so we're not able to use that as a power source in our homes. But electrical engineers develop ways to use power for specific applications like CD players, TVs, and video games. All those things
We know
are what
about all
electrical
those
engineers design and develop so that we can use that power.
What do we call electricity that runs through our house?
That's used as electric current. We use electric current in electric circuits to be able to develop ways to use electricity for useful applications.
What is an electrical circuit?
All your lights, all your TVs, your stereos, everything
Is on
has
a
to be
circuit.
hooked up on a circuit.
Okay, can you show me like a little cool example of a circuit?
Right. Basically what an electric circuit is made up of 3 basic components. We have a power supply, which is typically a battery or it could be a motor, and you have electron carrying conductors, which is usually copper wire, which is represented here. And then inside the circuit you have to have some type of resistance. The resistance might be a light bulb or the sound coming out of your speakers.
Sure, so we can actually use this power.
Use this power to do
something.
some type of activity. And you also have an open and closed switch, just much like you do on the wall when you walk into a room.
Yeah, because the lights aren't always on. In fact, you always don't want to leave your lights on. You want to turn them off.
Exactly.
So that's what the switch is for.
And what you're doing is you're opening the circuit so there's no place for current to flow. So basically when you walk into the room and you flip your light switch, you're closing the path and you have a closed circuit.
Okay, when it's closed, I always like, this is what I teach my kids, it's a closed circuit. It's like a circle.
That's right.
Like it's always flowing.
It's continuously running around in a circle.
Okay, but you can break it by opening it up.
Right.
And turning the light off.
Right. Basically we have electrons flowing out of this terminal. They're flowing through the wire, they go through the bulb, they come through this wire, through the switch, they come through this resistor here, they come back into the negative terminal, and they keep doing this continuously until the battery goes dead.
Or until you flip it off.
Or until you flip it off.
What's this guy again?
This is a resistor. Basically, if you go ahead and turn that knob right there, you are adding resistance to the circuit, which
Hey,
decreases the number of electrons flowing through the circuit, and as you notice, you dim the light.
you must have been through a lot of schooling to become an electrical engineer. You're pretty smart. You know a lot of stuff about electricity.
Thanks, you have to go to college for quite a while to be able to do that. You have to go to college.
Thank you so much, Rick.
Thanks a
I
lot.
really appreciate it.
Thanks for having Brain Stew out at NASA, and hopefully you guys will come back and we can do something neat again sometime.
We will. Thanks a bunch.
Thanks. Bye.
So now you know all about,
Electricity, electric circuits, and electric currents.
plus you know how electricity gets from the power plant to your home and how to be safe around electricity. But wait, there's more. We have an experiment performed by a kid whose brain is filled with facts on electricity. Plus, we visit our local library to get even more information on electricity. Hey, don't use your knowledge about electricity to turn off your TV. Brain Stew will be right back, I promise.
Can a balloon actually move water without touching it? Let's find out. This is all you need for this easy but awesome experiment. A small balloon and a water faucet. And here's the procedure. First, you blow up the balloon and then you put a knot in the end of it. Next, you need to turn the faucet on. Not like that, not a thick stream, a thin stream like that. Next, you take the balloon and you rub it up and down on your arm about 10 times. Next, you take the balloon and you hold it very close to the stream of water. Don't touch it, just hold it real close. The balloon actually moved the water without touching it. Why'd that happen? I'll tell you. When you rub the balloon on your arm, electrons from your hair jump or move to the balloon. The balloon now has a negative charge because it received extra electrons from your hair. The water has no charge. It is neutral. This means the water has the same number of electrons and protons. Holding the negative charged balloon near the neutral water causes the electrons in the water to move away because like charges repel. The water then has a positive charge. When a positive and a negative charge are placed close together, they attract. The water was attracted to the balloon because of electricity.
I gotta thank Carol at Virginia Power for letting us visit the Surrey Nuclear Power Plant. That was a totally enlightening experience. Oh yeah, don't forget about Rick at NASA. You know what? If you stay in school, who knows? Maybe you too can be an electrical engineer. Well, I got a bolt. Yeah, bolt, that means like I gotta go. You never heard of that before? Anyway, not to worry. I'll be back next week, and I'll see you and that big brain of yours then. No one, not even me, can see them. Oh, where are my glasses?
How can electricity come from the...
That was a totally enlightening experience. Let me say that again, sorry. That was...
Yeah. Like...
Hey, thanks for all the letters I've been receiving. Here's one now. Zoomed in by Kevin. Hey, thanks for all the letters I've been receiving. Here's one now.
Wait a minute.
Brain freeze.
First, oh gosh.
Zoomer number 2.